Topics in the History of Mathematics, MA 290, Cassette 3, Side 1, Indian Mathematics. This cassette is linked to your work in Unit 5, and you should listen to this before reading Unit 5, Section 2. You should have your cassette notes open in front of you. This will help you with some of the quotations from Indian mathematics used in this talk. As the Hindu Arabic numerals were discussed in TV2, they will not be referred to here. But in this talk by Graham Flegg of the course team, you'll be introduced to 3 key figures in Indian mathematics, and you'll hear about the Indian influence on Arab mathematics.
The city of Baghdad on the banks of the river Tigris lies in the fertile crescent of Iraq, between the Iranian and Syrian deserts. What's today called the Old Town was for some 500 years in the Middle Ages the headquarters of the famous Caliphate, known to us from childhood through the stories of the 1001 Nights. Its geographical situation made it an important centre of trade, for it lay directly on the route from the Mediterranean to India. Travellers from the west would rejoice to see its splendid palaces and gardens after a long and dusty trail across the Syrian desert. And those from the east would no less welcome its luxury and splendour after a much longer journey which included the crossing of the inhospitable desert of Persia. Because of the difficulties of the journey by land, much of the trade between India and the capital city of the Caliphate came by sea from the ports of the western Indian seaboard, via the Persian Gulf and the towns at its northernmost limit, then by land or river to Baghdad itself. The arrival of a large caravan bringing merchandise from the Far East must have been a noteworthy event in the Middle Ages. And interest was aroused not only among the merchants and officers of the Caliph, but amongst the scholars also. For along with all the usual paraphernalia of trade, there might be found a Sanskrit manuscript, which the Caliph's officials would pass on for study at the House of Wisdom, a principal centre for Arab scholars set up by the Caliph himself, with its own extensive library containing Greek and Persian and Arabic works, and its observatory for scientific study. The House of Wisdom was created in the early 9th century, but the trickle of Indian manuscripts had begun some half a century earlier, indeed almost from the founding of the city itself in the 760s. One of the first Indian works to arrive in Baghdad was an astronomical work by the 7th century astronomer and mathematician Brahmagupta. It's generally called the Brahmasvat Siddhanta, which means the correct astronomical system of Brahma. It may well have been this work which first acquainted Arab scholars with the Hindu numerals, which were to become those that we use today. Brahmagupta was the chief astronomer at the observatory of Ujjain in the central part of northern India, and his work is the best known of the Indian Siddhantas, astronomical writings, representing the height of their development, which had begun in the 3rd century. It was to become widely known in India, and many commentaries were written on it. Its translation into Arabic by Al-Fazari, together with an Arabic translation of Ptolemy's Tetrabiblos, 4 books from the Greek, mark the beginning of the Arab interest in astronomical writings. It's interesting that it was Ptolemy's astrological work, the 4 books, that was translated first, rather than his astronomical work, the Almagest, which was only translated later. Much of the 21 chapters of the Brahmasvat Siddhanta still exist in their original Sanskrit. About 3/4 of the work is on astronomy, but at least 3 chapters are on mathematics, which was called Ganita, literally calculation. A clear distinction is made between arithmetic and algebra. Brahmagupta called algebra Kutaka Ganita. Kutaka refers to a particular equation, which we would write as ax plus by equals 1, and which was the basis for solving certain types of problem. It's sometimes referred to as the pulverizer. Later Indian writers call algebra Bija-ganita, calculation by analysis, or Avyakta-ganita, calculation with unknowns, as opposed to Vyakta-ganita, calculation with knowns, that is, arithmetic. Brahmagupta begins his chapter on algebra as follows.
Since questions can scarcely be known without algebra, I shall therefore speak of algebra with examples. By knowing the pulverizer, zero, negative and positive quantities, unknowns, elimination of the middle term, equations with one unknown, factum, and the square nature, one becomes the learned professor amongst the learned.
By factum and the square nature, Brahmagupta is referring to solving problems using the equation which we would write as nx squared plus 1 equals y squared, where n is an integer that's not a perfect square. We can tell from this quotation how important algebra had become in India by the 7th century, and that within algebra such problems were of considerable significance. It's in the chapter devoted to algebra that we find general algorithmic rules extended from positive and negative quantities to zero, the earliest known general treatment of its properties.
The sum of cipher and negative is negative. Of positive and naught, positive. Of two ciphers, cipher. Negative taken from cipher becomes positive, and positive becomes negative. Cipher naught. The product of cipher and negative, or of cipher and positive, is naught. Of two ciphers, it is cipher. Cipher divided by cipher is naught. Positive or negative divided by cipher is a fraction with that as denominator, or cipher divided by negative or positive.
Thus Brahmagupta is somewhat vague about division by zero, or cipher as he also calls it, simply leaving it as a fraction having zero as its denominator. Equally, zero divided by a number is to be left in its fractional form. Let's now look briefly at quadratic equations in the Brahma Siddhanta. We find three specific rules. This is the first.
The absolute quantities multiplied by 4 times the coefficient of the square of the unknown are increased by the square of the coefficient of the middle. The square root of the result being diminished by the coefficient of the middle and divided by twice the coefficient of the square of the unknown is the middle.
Let's just listen to that again, but at the same time thinking of a quadratic of the form ax squared plus bx equals c.
The absolute quantities multiplied by 4 times the coefficient of the square of the unknown,
that's just 4ac,
are increased by the square of the coefficient of the middle.
that's b squared plus 4ac.
The square root of the result,
That's root b squared plus 4ac.
being diminished by the coefficient of the middle
That's minus b plus root b squared plus 4ac.
and divided by twice the coefficient of the square of the unknown
All over 2a
is the middle.
is the unknown x. In other words, remembering that we had c on the right-hand side of our equation, this is precisely our familiar formula for the solution of the general quadratic, and Brahmagupta's other rules are also equivalent to modern formulae. However, all this isn't new. The same general rules, expressed in words, can be found in an astronomical work of Aryabhatta, who dates from the end of the 5th century. Like Brahmagupta, Aryabhatta devotes part of his work to Ganita, calculation. The chapter concerned is quite wide-ranging. It takes in the basic arithmetical operations, together with square and cube roots, areas and volumes of basic figures, progressions, some trigonometry, and a discussion of the decimal place value principle, which evolved in India at least by the 6th century. We can only just dip here and there into this work, which is called the Aryabhatiya. Let's begin with the circle. Having given a formula for the area,
Half of the circumference multiplied by half of the diameter is the area of a circle.
he later goes on to give a value for pi.
Add 4 to 100, multiply by 8, and add 62,000. The result is approximately the circumference of a circle of which the diameter is 20,000.
This value, 62,832 over 20,000, is 3.1416. But was this remarkably accurate value for pi Aryabhata's own work? This seems unlikely. It's identical to that of the Chinese geometer Liu Hui, who lived in the 3rd century, and it's probable that they had a common source. Indeed, Aryabhata acknowledges indebtedness to predecessors.
By the grace of Brahma, the precious sunken jewel of true knowledge has been brought up by me from the ocean of true and false knowledge by means of the boat of my own intellect.
A somewhat poetic and oblique way of saying that he was able to discern the truth from the ocean of truth and falsehood to be found in earlier writers. A convincing case has been made by Professor van der Waarden that the common source for the value of pi in the works of both Liu Hui and Aryabhata is to be found in the astronomical system of Apollonius. Now we may ask ourselves how Greek works were able to reach India and China at a time when travel was difficult and cultures often so distinct. Well, we've been talking about the links between India and Baghdad in the 8th century. This was greatly stimulated by the rise of Islam and the extension of its empire, which stretched eventually from Spain in the west, via North Africa and the Middle East, to the Indian subcontinent. But we must remember that a much earlier empire had also reached out to India. This was the empire of Alexander the Great of Macedonia, who with his eastern conquests had spread Greek civilization far beyond the eastern Mediterranean as early as the 4th century BC, and had thus paved the way for knowledge of Greek works to be extensively disseminated. Indeed, it seems most likely that the 0, without which the decimal place value system couldn't have evolved in India as it did, wasn't an independent Indian invention, but was taken by Indian astronomers from the Babylonian sexagesimal system used in Greek astronomical works. But let's return now to the Aryabhatiya itself. We find a discussion of arithmetical progressions, including instructions for calculating the sum of any n successive terms.
The desired number of terms minus 1, halved, plus the number of terms which precedes, multiplied by the common difference between the terms, plus the first term, is the middle term. This, multiplied by the number of terms desired, is the sum.
So the sum is given by the middle term of the n successive terms, multiplied by n, and there's an explicit rule for finding that middle term. One somewhat obscure passage in the Aryabhatiya came to be known as Aryabhata's rule. It begins as follows.
Divide the divisor corresponding to the greater remainder by the divisor corresponding to the smaller remainder. The residue being mutually divided, the last quotient should be multiplied by an optional integer and then added or subtracted by the difference of the remainders.
Various commentators tried to discover the problem for which this rule is a solution. It's quite difficult, particularly as the rule is greatly abbreviated and has to be filled in before a full understanding is possible. It turns out that the rule solves the problem, find a number which, when divided by two given numbers, will leave two given remainders. The rule permits us to find the smallest number satisfying the given conditions. Aryabhata is the first Indian mathematician to formulate such problems, which are then taken up extensively by later writers. Let's turn to something not in Aryabhata's work, but found first in the Brahmasfud Siddhanta. This is, to find all quadrilaterals which can be inscribed in circles with integral diameters, whose sides, diagonals, perpendiculars, segments, and areas are also whole numbers. By segments is meant segments of sides and diagonals which we get from intersections with the perpendiculars from the vertices, and from the diagonals intersecting each other. Brahmagupta gives a simple rule involving calculations using the sides of two right-angled triangles. The quadrilaterals so obtained still bear his name. They're called Brahmagupta quadrilaterals. There were, of course, many Siddhantas, astronomical works, written between the time of Aryabhatta and that of Brahmagupta. Most of these include mathematical chapters, the greater part of which were inspired by the needs of astronomy. This applies especially to Indian trigonometry, but less so to the arithmetic and the algebra, where a number of the problems raised relate to everyday life or are purely fanciful. Let's look at one innovation of Indian trigonometry, the change from Ptolemy's chords of arcs to half-chords. Ptolemy's chords are calculated on the basis of a circle of diameter 120 units. In an Indian astronomical work written some half a century before the Aryabhatiya, these were changed to half-chords with 120 units for the radius, but these were still associated with the full arcs. It was Aryabhatta who introduced the two really significant changes. First of all, he associated the half-chord with half the arc, which is an important step towards our familiar sine of an angle. Then he changed the radius from 120 to 3,438 units. He obtained this number by dividing the number of minutes of arc, corresponding to the whole circumference, that's 360 times 60, by 2 pi, with pi taking his value of 3.1416. In fact, the radius you get is slightly less than 3438, but it comes to it to the nearest whole number. Aryabhatta's table of sines is presented at intervals of 3 degrees 45 minutes, giving 24 sines in all. He gives two methods for computing these, but following van der Waarden's arguments, it seems likely that the table was originally computed directly from Greek sources by halving the chords. The argument for a Greek origin for Indian trigonometry, apart from the half-chords, is strengthened by the fact that in the earlier Siddhantas, up to the end of the 5th century, astronomical calculations used Alexandria for the meridian. We now move on some 5 centuries for the third and final Indian mathematician to be discussed here. This is Bhaskara, or more strictly, Bhaskara II, who lived in the 12th century and was the last of the great medieval Indian mathematicians. In 2 of his works, the Lilavati and the Bijganita, he takes up Brahmagupta's rules for operations involving zero, extending his result for division by zero. Instead of leaving it as a quantity with zero as denominator, he expands on its value.
In this quantity, consisting of that which has cipher for its divisor, there is no alteration, though many may be inserted or extracted, just as no change takes place in the infinite and immutable God at the period of the destruction or creation of worlds, though numerous orders of beings are absorbed or put forth.
Thus, Bhaskara clearly demonstrates that he knows that finite over zero yields the infinite, and that the infinite, plus or minus the finite, remains unchanged. He also gives a number of examples of calculations of naught over naught, which clearly suggests that he had some concept of infinitesimals as limits. For Brahmagupta, as we've seen, naught over naught is just naught. Both Bhaskara's works contain many problems illustrating determinate and indeterminate linear and quadratic equations, surds, progressions, applications of Pythagoras' theorem, and so on. But of special interest is his understanding of algebra as the science of symbols. In the Bijganita he writes,
Analysis is certainly the innate intellect assisted by the various symbols, which for the instruction of duller intellects has been expounded by the ancient sages who enlighten mathematicians as the sun irradiates the lotus. And that has now taken the name algebra. Because intelligence is certainly the real analysis, symbols are its helps.
The relationship between the two branches of mathematics, arithmetic and algebra, is also spelt out.
The science of calculation with unknowns is the source of the science of calculation with knowns. Mathematicians have declared algebra to be computation attended with demonstration. Else there would be no distinction between arithmetic and algebra. The method of demonstration is always of two kinds, geometrical and algebraic.
Thus, for Bhaskara, mere rules for solving equations belong to arithmetic. Algebra demands that such rules be justified, both geometrically and algebraically. Thus, having given a rule for the solution of a quadratic indeterminate equation involving the product of the two unknowns, and an example, he then provides first a geometrical and then an algebraic proof for his method, though he does suggest that the algebraic proof has geometrical origins. It's in the whole area of indeterminate analysis that Bhaskara is at his best. A notable example is his extensive treatment of equations of the form nx squared plus 1 equals y squared, which had appeared also in Brahmagupta, and which were to be taken up again in Europe in the 17th century by Fermat. Bhaskara deals with the cases where n is 8, 11, 32, 61, and 67.
Tell me, O mathematician, what is that square which multiplied by 8 becomes, together with unity, a square? What is that number whose square multiplied by 67 or 61 and then added by unity becomes capable of yielding a square root? Tell me, O friend, if you have a thorough knowledge of the method of the square nature.
Bhaskara gives more than one method of solution, including a cyclic formula not found in earlier writings. He uses this to compute the solutions for the larger values of n. The computations are a remarkable feat of arithmetic, which today we would certainly give to a computer. Thus, for example, n equals 61 leads to a solution where x is a 9-digit number and y a 10-digit number. That is, he's calculating in hundreds and thousands of millions. The 9 centuries from the time of the earliest Siddhantas to that of Bhaskara represent the highest achievements of the Indian mathematicians of the Middle Ages. After Bhaskara, there is a marked decline. Before the astronomical works, and roughly contemporary with the ancient civilizations of the Near East, Babylonia and Egypt, we find some practical arithmetic and geometry, interspersed amongst stories, songs, liturgical chants and sacrificial formulae in the Vedic literature of the upper Indus basin. Somewhat later, from the 1st millennium BC, in the so-called Books of the Rope, we find Pythagorean triples, approximations for root 2, rules for the construction of geometrical figures, straight edge and compass constructions, and attempts at constructions for squaring the circle. But we must be careful to remember that the mathematics of this period has to be extracted from works often written in verse form, which are also extensively devoted to folklore, mysticism, invocation of the gods and such like. Indeed, they were first and foremost religious works. This tradition extends also to the Siddhantas. It's perhaps hard to think of tables of signs in verse form, but this is precisely what we would have in, for example, the Aryabhatiya. Bhaskara's Lilavati got its title, which has nothing to do with mathematics, from the name of the writer's daughter, who, so it is said, lost her opportunity to marry because the time wasn't propitious according to her father's astrological calculations. She had his mathematical work named after her for consolation. As to the source of Indian astronomical and mathematical knowledge, this is attributed not to any human strivings, but to revelation by the sun god. The story is told at the beginning of one of the most famous of the Siddhantas. A great demon called Maya performed rites in propitiation of the sun, seeking to know the mysteries of science. To him the sun spoke.
Thine intent is known to me. I am gratified by thine austerities. I will give thee the science upon which time is founded, the grand system of the planets. No one can endure my brilliancy, and for communication I have no leisure. This person, which is a part of me, shall tell thee the whole. Go therefore to the city of Romaca, there undergo incarnation as a barbarian, and I will impart to thee this science. Thus having spoken, the god vanished, having given instructions to a part of himself. This latter person thus addressed Maya. Listen with concentrated attention to the ancient and exalted science which has been spoken in each successive age to the great sages by the Sun himself.